All right, so we're all living through it, right? The AI revolution. It feels like the next great leap for humanity, a future full of just incredible progress. But what if? What if this revolution is hiding a really big flaw? A flaw that could mean we're repeating one of the biggest mistakes in history.
Think about it, the first industrial revolution. It ran on steam and steel. Those were the raw materials that literally reshaped the world. And today? Well, our engine is AI, and its fuel is data. The parallel seems pretty simple, right? But it goes so much deeper, and hidden inside it is a huge warning about the future we're building right now. Because, you see, while that first revolution brought all this unprecedented growth, it also came with a hidden and really critical flaw in how we even measured progress. So that leads us to the big question. Are we about to make the exact same mistake all over again? Okay, so to really get a handle on the risk we're facing, we need to start with a tale of two revolutions. So let's do a super quick history recap. The first revolution, that gave us mechanical production, right? Then the second, powered by electricity, brought us mass production and the assembly line. And the third, the digital revolution, that was not about computers and automation. Each one completely changed our world. But there's a metric that tells a totally different story about these revolutions, a kind of hidden story about their true cost. And it's a concept that puts our current AI boom into a really startling new light. It's called the economic productivity of energy, or EPE for short. Now, it sounds complicated, but it's really not. It's just the amount of economic value, think GDP, that we get from one unit of energy we use. So a simple way to think about it is, for every kilowatt hour of energy we burn, how much wealth do we actually create? It's a super powerful way to measure how efficient we truly are.
And this is where the story gets really interesting. Just look at what happened to EPE during that first industrial revolution. Before all the factories and steam engines, it was at 0.21. But as those engines fired up, EPE collapsed. I mean, it was nearly cut in half. The economy was booming, sure, but our ability to actually generate value from energy got worse, not better. And why? Because the technology was being adopted for profit, not for efficiency. Now, the later revolutions, they were different. They actually avoided this collapse, and for one really crucial reason. With things like electricity and microelectronics, the deep scientific understanding came before the technology was rolled out everywhere. This science-first approach meant efficiency was kind of baked in from the start, and that let EPE trend upwards. And that right there is a vital lesson from history, which of course brings us to today. Because when we take this EPE lens and apply it to our AI revolution, the parallel to that first messy, inefficient revolution, well, it becomes alarmingly clear. And this is exactly why some researchers are calling AI a pre-scientific engine. I mean, think about it. Just like those first steam engines, we're scaling it and monetizing it at this breathtaking pace simply because it's profitable, all without a full scientific grasp of its true energy cost or its consequences on a bigger system-wide level. And the energy costs? They are absolutely staggering. Get this. Generating a single image with AI can be, on average, 60 times more energy intensive than just generating text. 60 times. That's the kind of hidden, exponential cost behind these creations that seems so effortless. So where does all that energy actually go? Well, for a model like GPT-4, the vast majority of it is spent up front. That training phase, the massive process of teaching the AI everything it knows, can have a carbon footprint up to 15 times higher than the footprint of actually using it for an entire year. It is a colossal front-loaded energy investment before you even get started. And this really puts the stakes in stark terms. The risk here is that our overall energy efficiency, our EPE, may once again start to decline. We could be repeating the big mistake of the first industrial revolution at the very moment when global sustainability is more critical than ever before. But, the problem isn't just about the energy AI consumes. It's also about the fuel it runs on. If AI is the engine, then you've got to think of data as its steel, the raw material that makes the whole thing possible. The World Economic Forum puts it perfectly. They say the rails of the AI revolution aren't made of code. They're made of data. Without a constant supply of high-quality structured data coming in from the real physical world, the entire system just grinds to a halt. And yet, for all the hype, here's a shocking reality check. According to MIT, a whopping 95% of industrial AI pilot projects fail. They never get fully implemented. They just don't work in the real world. So what is going on here? Well, the number one reason is poor data quality. It's that simple. We've built this incredibly powerful engine, but we haven't built the high-fidelity steel rails for it to run on. We're basically asking AI to operate with this incomplete, messy, and often analog view of the physical world. It's a powerful engine going absolutely nowhere fast. So, okay, we're at this critical crossroads. We're facing a potential energy crisis on one hand and a massive data bottleneck on the other. But here's the thing, history doesn't have to repeat itself. The outcome here depends entirely on the choices we make, starting right now. The path forward really requires moving on two parallel tracks. First, creating smarter policy to guide this revolution, and second, developing smarter technology to make AI itself more efficient and sustainable. All right, on the policy side, the big goal is to make all these invisible costs visible. That starts with making EPE an official metric in sustainability reports. It means we have to mandate transparency so companies actually have to disclose the energy cost of their AI models. And crucially, it means tying government incentives to real, measurable gains in energy productivity. Because at the end of the day, if you can't measure it, you can't manage it. Then there's the technology side, where there are also some really clear steps we can take. We can optimize the hardware, using specialized computer chips that are designed specifically for AI and are way more energy efficient. We can, of course, power these massive data centers with renewable energy, and we can innovate on the AI models themselves, building leaner algorithms that do more with less, like the mixture of experts approach, which is really clever. It only activates the parts of the AI model that are needed for specific tasks. Ultimately, this is the great paradox of AI, isn't it? It's a technology that both threatens our energy productivity and, at the same time, holds the potential to vastly improve it. It's not destined to be one or the other. The path we choose, and whether we actually learn from the costly mistakes of the past, that's all going to be decided by the actions we take today. So the real question is, which path will we choose?